Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1. Write isotopic symbols in the form of AZX for the isotope of copper with 34 neutrons. So first, let's try to define AZ and X when used in this context. So X is pretty easy. It is pretty much just our symbol, which tells us which element that we have. A is atomic mass. And atomic mass is actually equal to the number of protons plus our number of neutrons. And finally, Z is our atomic number. And the atomic number is the same thing as our number of protons. Okay, so now that we defined everything for this form, let's start off by answering our question. So we have a copper isotope with 34 neutrons. So copper has the symbol of Cu. So we already know that our X will just be equal to Cu. And now we can look up copper on the periodic table and find out its atomic number. Okay, so let's pull up the periodic table. And copper is found here, and its atomic number is 29. So that means there are 29 protons. And the question says that this copper isotope has 34 neutrons. So let me write that down as well. And we have our Z is 29, which is also equal to our number of protons. So now let's plug these values in our equation for atomic mass. So again, atomic mass is our number of protons, which was 29, plus our number of neutrons, which is 34. So 29 plus 34 is equal to 63. So now we have all of our values for A, Z, and X. So therefore, A was 63, Z is 29, and our symbol is Cu. So now let's see what the junior tutor said. Atoms are made up of subatomic particles, namely protons, electrons, and neutrons. Protons are positively charged, and neutrons have no charge and can be found at the nucleus of an atom, while electrons are negatively charged and they surround our nucleus. Isotopes are atoms of an element that have a different number of neutrons in the nucleus. Isotope notation is typically written as AZX, where X is the symbol of the element, A is the atomic mass, which is the number of neutrons plus the number of protons, and Z is the atomic number, same with the number of protons. In this question, we are asked to find the isotopic symbol for copper with 34 neutrons. So first they wrote out the symbol, and they found the atomic number from the periodic table, which was 29. And finally, they calculated the atomic mass by adding 29 and 34 to get 63. So they got the same answer, and this solution is correct. Okay, question number 2. 15 milliliters of radiator liquid, which is a mixture of water and ethylene glycol, from a car has a mass of 15.69 grams. Part A, calculate the density of the radiator liquid, show how you calculated it, and also show the units with the answer. Part B, based on the calculation above, is the density of ethylene glycol greater than or less than that of water? Explain your answer. And finally, for C, determine the mass percent of ethylene glycol in the mixture. So let's first do part A. So let's recall the equation to find density. Density is equal to mass over volume. And in this question, it looks like we are given both. So then we can find the density of our radiator liquid. So I'll just denote it as rad liq is equal to the mass, which is 15.69 grams. And the volume is 15 milliliters. So 15.69 divided by 15 gives 1.046 grams per milliliter. Okay, so now let's do part B. Based on the calculation above, is the density of ethylene glycol greater than or less than that of water? So first, let's recall the density of water. And it's actually pretty simple. It's around 1 gram per milliliter. So that means when we have 1 milliliter of water, if we were to weigh it out on a scale, it would also be equal to 1 gram. So that's pretty easy to remember. And when we have this mixture of water and ethylene glycol, we have a higher density than that of water. So therefore, ethylene glycol is more dense. And now let's do part C. Determine the mass percent of ethylene glycol in the mixture. Okay, so first let's make some assumptions to help us answer this question. We'll assume that X is the mass of ethylene glycol. So in a mixture containing only water and ethylene glycol, we know that 1 minus X is equal to the mass of our water. So these are based on percentages. And if we had 100% of our mixture, then the mass is X, then we know that 100 minus however much of the ethylene glycol there is will give us the mass of water. So now let's plug it into this equation where we know we're trying to determine the mass percent of ethylene glycol in the mixture. So first we need the density of pure ethylene glycol. So let's look that up. And you get around 1.11 grams over centimeter cubed, which is the same thing as grams per milliliter. So now let's make an expression to find out the mass percent of ethylene glycol. So we know the density of ethylene glycol is 1.11, and the mass percent of ethylene glycol is X. And we know the density of water is just 1. And the water is described as 1 minus X. And if we were to add these values up, we get the density of our radiator liquid. So now let's just plug that value in. 1.11x. And I'll just simplify this. This is the same thing as 1 minus x is equal to what we found in part A, which is 1.046. So now let's just solve for x. You end up getting 0.11x is equal to 0.046. So x is equal to 0.4182. So therefore, our mass percent of ethylene glycol is 41.82%. So now let's see what the junior tutor said. And in this problem, the given quantities are the volume of radiator liquid, which is 15 mils, and the mass of car. Oh, I guess the mass of the radiator liquid is 15.69. So when finding density, it's just mass divided by volume, and they also got 1.046 grams per milliliter. And then they wrote out the density of water is 1000 kilogram per meter cubed, which is the same thing as 1 gram per mil. So they converted their answer from the previous step to kilograms per meter cubed, and they found that the density of ethylene glycol is greater than the density of water. Okay, so that's correct. And now to determine the mass percent of ethylene glycol in the mixture, again, they just use a different units than we did. They did kilogram per meter cubed, but they have the same sort of setup to find the mass percent of ethylene glycol. Okay, and they ended up getting the same answer, which was around 41.8%. So this solution is correct. Question number 3. When methane is burned with oxygen, the products are carbon dioxide and water. We produce 18 grams of water from 8 grams of methane and 32 grams of oxygen. How many grams of carbon dioxide were produced in the reaction? So first, let's write out the formula for methane. So if we try to analyze the word methane, it has the prefix of meth, which tells us that there is only one carbon. And even the fact that it ends in ane tells us that there is a single bond. But since there's only one carbon, we can already kind of assume there's only single bonds. So therefore, the chemical formula of methane is CH4. And methane reacts with oxygen gas, which is in its diatomic state, so it's O2. And this produces carbon dioxide and water. Okay, so now we need to balance out this reaction. We have one carbon on both our products and reactant side, but on our product side, we only have 2 atoms of hydrogen, but on our reactant side, we have 4. So I'm just going to put a coefficient of 2 in front of my water. And now we have our hydrogens that are balanced and 4 oxygens on our product side and only 2 oxygens on our reactant side. So I'm also just going to put a 2 in front of our oxygen. So now we have our balanced equation. And they give us the following grams of methane. So we started off with 8 grams of methane. And we have 32 grams of oxygen. And they also told us that we produced 18 grams of water. So this question actually gives us more information that we needed. So typically we would find out the number of moles of both of our methane and oxygen and do a whole bunch of different steps to try to find out which one was the limiting reagent. And then from there, find out how much product was formed. But luckily for us, they gave us the mass of water that was formed, which was 18 grams. So all we need to do is find the number of moles of water in 18 grams, and then relate that to find the number of moles of carbon dioxide, and then we can convert that to grams. So again, just to sum it up, step 1 is to find the number of moles of water. So we know the mass is 18 grams, and we just need to first find the molar mass of water, which is equal to 2 times the molar mass of hydrogen plus the molar mass of oxygen. So these values are found on your periodic table. It's 1.01 grams per mole for hydrogen and around 15.99 grams per mole for oxygen. So this gives us a molar mass of around 18.02 grams per mole. So now to find the number of moles, it's just going to be the mass over molar mass. So the mass of water is given in the question, 18 grams. the molar mass is what we just found to be 18.02 grams per mole. And now if we divide this, we get the number of moles of water equal to around 0.999 moles. Okay, so step 2 is to now find the number of moles of carbon dioxide using mole ratios. So we know that the number of moles of water that was formed in this reaction was 0.999. And if we multiply this by the ratio where 1 mole of carbon dioxide is formed and 2 moles of water is formed in this reaction as well, then we just need to divide our number of moles of water by 2. And we know we did it correctly if you see that our units for the moles of water cancel out, and we're left with moles of CO2, and you get 0.499 moles of CO2. And now step 3 is to find the mass of CO2. So if we rearrange this equation where number of moles is equal to mass over molar mass, we can find mass by multiplying number of moles by the molar mass of carbon dioxide. So the number of moles we found in our previous step, 0.499 moles of CO2, and the molar mass of CO2 is around 44 grams per mole. And we get a mass of 21.98 grams. So this is our final answer. Okay, so the junior tutor said, let us first write the balanced chemical equation. Methane is a compound with a chemical formula of CH4. And they wrote out water, carbon dioxide, and oxygen. And then they balanced their equation and put the coefficients of 2 in front of oxygen and water. So now they want to... Okay, so this is what I mean about how they added some additional information. So these steps aren't really needed because, as you can see, we are able to find the mass of CO2 just by using the mass of water. But still, this is how you would do it if you want to do it the long way and get all your steps in. Given the mass of methane and its molar mass, you can find the number of moles of CH4. You can do the same thing for oxygen. Calculate the number of moles of water, which they did as well. They got 1. Use the mole ratio of oxygen and carbon dioxide to get the number of moles of carbon dioxide. Okay. And then calculate the mass of carbon dioxide produced. So notice that they found the number of moles of both oxygen and methane, but they didn't even really use it in their final answer. They just ended up using the number of moles of water in the end. But they still ended up with the same answer of 22 grams of carbon dioxide. So the solution is correct. Since we know the mass of water produced, we don't have to find the number of moles of CH4 and O2. If we were not given the mass of water, then those values would be useful, and we can determine the limiting reagent as well, and etc. Add some spelling mistakes. Yep. Let me just put this in brackets. But this solution is still correct. Okay, so question number 4. Carvone is a principal component of caraway and dill seed and is used as a food flavoring agent. Calculate the molality of a solution that contains 1.73 grams carvone and 18.5 milliliters of ethanol. And the density is given 0.7893 grams per mil. Assume that carvone is non-volatile at the normal boiling point of ethanol and that it is a non-electrolyte. So first, let's write down everything we know in this question, just because it will help us later on when we do calculations. So for carvone, we know that the mass is 1.73 grams. And let's also calculate the molar mass of carvone. So it's C10H14O. And to find its molar mass, it's just going to be 10 times the molar mass of carbon plus 14 times the molar mass of water plus the molar mass of oxygen. So these values are just found on your periodic table. Carbon's molar mass is 12.1 or 12.01. Hydrogen's molar mass is 1.01 and oxygen's is around 16. So we get a final molar mass of 150 grams per mole. Okay, so that's everything given for carvone. And on this side, I'm just going to write down everything given for our ethanol. We know that the volume of ethanol is 18.5 milliliters. And we're also given the density of ethanol as well, 0.7893 grams per milliliter. Okay, so let's use a different color and start answering the question. Step 1 is to find the number of moles of carvone. So since we have both mass and molar mass, we can use the equation number of moles is equal to mass divided by molar mass. So our mass is 1.73 grams, and the molar mass is 150 grams per mole. This gives us a number of moles of around 0.0115 moles. So step 2 is to find the mass of our solvent. mass of solvent. So let's recall that density is equal to mass over volume. So if we rearrange this equation, we can solve for mass by multiplying the density, which is 0.7893 grams per milliliter, by the volume, 18.5 milliliters. And notice that our units for mils will cancel out, and this gives us the mass of our solvent, which is around 14.6 grams. And another step here is to convert this to kilograms, because molality is equal to the number of moles divided by the kilograms of solvent. So we just convert to kilograms by dividing this value by 1,000, because 1 kilogram is equal to 1,000 grams. So now grams will cancel out, and our kilograms is 0.0146 kilograms. And now we have everything we need to find the molality of this solution. So again, molality is just equal to the number of moles divided by the kilograms of solvent. And we have both of these. Number of moles was 0.0115 for our solute, which was carbone, and the mass of the solvent is 0.0146 kilograms. So now our molality is 0.788 moles per kilogram. Okay, so the junior tutor said that carbone is found naturally in essential oils, but is most abundant in the oils from the seeds of caraway. In this problem, the given quantities are the following. So they also wrote everything down, and they're asked to calculate molality of the solution. So this is the number of moles of solute per kilogram of solvent. And first they found the number of moles of carbone. They calculated the molar mass of carbone and also got 150. And then they calculated the number of moles in the same way and got 0.0115 moles. For the mass of the solvent, they multiplied density and volume, got 14.6 grams, and then converted it to kilograms. And then finally, to find the molality, he divided number of moles with the kilograms of solvent, and they also got around 0.79. So this solution is correct. Okay, so question number 5. What is the oxidation for Rb2SO3, so rubidium sulfate? So I think they mean oxidation states. I'm just going to write oxidation states. And we have rubidium, and we have SO3. So first let's look at rubidium. So if we go to the periodic table, we can find rubidium in group 1A. So rubidium is in group 1A. So therefore, its oxidation number is equal to +1. And for oxygen, there is a rule that states that the oxidation number of oxygen is typically -2. The only exception is if it is involved in a peroxide. So then if it was a peroxide, oxygen would have the oxidation state of -1. But since it is not, then it has an oxidation state of -2. So I'm assuming we need to find the oxidation state of sulfur. So first, let's look at our two oxidation states that are given. We know that for rubidium, it has an oxidation state of +1. So when we have 2 atoms of rubidium, 2 times +1 is equal to +2. So this whole thing gives off a +2 charge. And in the case of the oxygen, it has an oxidation state of -2, but we have 3 atoms of oxygen. So overall, it's -6. So if we look at our compound, we'll see that it is a neutral compound. So that means sulfur needs to be an oxidation state that is able to neutralize the -6 plus 2, so -4. So therefore, sulfur needs to have an oxidation state of +4. Okay, so again, I'll just write down the oxidation states down here. Rubidium has a +1 oxidation state because it's in group A. Oxygen is not in its peroxide form, so its oxidation state is -2. And then we calculated the oxidation state of sulfur to be +4. So another way we can do this is if we analyze the sulfur atom, which has the formula SO3 2-. Another rule for oxidation states is that the sum of these oxidation states equals to the charge of the ion. So since this ion has a charge of -2, and again we know that the oxygen would be -2 times 3, which is -6, and we need an overall -2 charge, then this is another way that we can find the oxidation state of sulfur to be +4. Okay, so let's see what the junior tutor said. Oxidation refers to the loss of electrons of an element during a reaction resulting to an increase in the oxidation state. To determine the oxidation state, see the rules below per element. The oxidation state of rubidium is +1. Rubidium is an alkali metal, and it belongs to the first group elements. So the rule is that alkali metals always have an oxidation state of +1. Step 2, the oxidation state of oxygen is -2. Oxygen needs 2 electrons to follow the octet rule. So it's -2 in most compounds except in peroxides where its oxidation state is -1. And then note that the sum of the oxidation numbers for all atoms in a neutral compound is equal to 0. We will use this to get the oxidation state of sulfur. So they plugged all the values, well, they made an expression to find oxidation state of sulfur. and they showed that it needed to be +4. Okay, so this solution is correct. Okay, so question number 6. If there are 15 milliliters in 1 tablespoon, how many milliliters are contained in 3.5 tablespoons of liquid medication? Okay, so let's write down the conversion factor where 1 tablespoon is equal to 15 milliliters. And we want to know how many milliliters are contained in 3.5 tablespoons of liquid medication. So first, let's write down our unknown, which is X mils. And we want to know how many mils are in 3.5 tablespoons. So to solve for this, we'll make this equal to our conversion factor and have the same order of numerator and denominator. So whatever unit we're looking for will be on top, which is milliliters, and the units that we're trying to get rid of will be at the bottom. So this is tablespoons. So now all we need to do is solve for x. So if we multiply both sides by 3.5 tablespoons, you get the following. And our units for tablespoons will cancel out. And it's pretty much the same thing as dividing 15 by 3.5. And you get x is equal, or multiplying, sorry, you multiply 15 mils by 3.5, and you get x is equal to 52.5 milliliters. Okay, so the junior tutor said, given that 1 tablespoon is equal to 15 mils, then 3.5 tablespoons is equal to 52.5 milliliters. Okay, so this solution is correct. Okay, question number 7. What is Dalton's atomic theory? All right. Okay, so parts of his theory is 1, all matter is made up of atoms. Which are indivisible. So they're already in their smallest form. And part of his theory, again, is that all atoms of a given element are identical in mass and properties. So one carbon atom is identical to another carbon atom. And the third part of his theory is that compounds are combinations of two or more types of atoms. And finally, a chemical reaction can also be described as a rearrangement of atoms. Okay, so these points kind of sum up Dalton's atomic theory. So now let's see what the junior tutor said. Dalton's atomic theory states that all matter are made up of atoms. His theory was named the billiard ball model because of how he described the atom. Following are the postulates of his theory. All matter are made up of tiny indivisible particles called atoms. An atom cannot be further divided into smaller units. Atoms can neither be created nor destroyed. So that's true as well. Atoms of the same element are identical, while atoms of different elements are different in terms of characteristics like size, shape, and weight. Finally, atoms of different elements may combine in small whole number ratios to form compounds. Yep, so this solution is correct. Okay, so question number 8. For the structures below, show the setup and the calculation for the formal charge of each atom. For any atoms with non-zero formal charges, label the atoms on the structure with the charges. So they have the formula for formal charge, but I'll also just rewrite that. And then they have the two structures. And then they just want to kind of fill in this table. So let's start off with structure number 1. We have hydrogen single bonded to a carbon that is double bonded to a nitrogen with a lone pair. Okay, so this was given in the question already, but I'm just going to write it at the top here, that formal charge is equal to the number of valence electrons minus the number of non-bonding electrons. Wonder if I can fit very small here, minus the number of bonding electrons divided by 2. Yep, so that just barely fits. Okay, so now let's do it for our first structure and calculate the formal charge of our hydrogen. So if we look at the hydrogen atom, hydrogen has 1 valence electron, and there are no lone pairs on this hydrogen, so the number of non-bonding electrons is equal to 0. And there's 1 bond to the hydrogen as well, so that means there are 2 bonding electrons, and we divide this by 2. So 1 minus 0 minus 1 gives 0. So the formal charge for hydrogen is 0. So now let's do the same thing for our carbon. Carbon has 4 valence electrons. There are no lone pairs. So I think that this should be a triple bond. So I'm just going to draw that in. It's kind of hard to see in the sketch, so I think that should just be a triple bond since carbon needs 4 bonds. So again, there are no lone pairs, so we just put 0. And there are 4 bonds to carbon, so we have 8 bonded electrons in total, divided by 2. So we also get a formal charge of 0. And now let's do the same thing for nitrogen. Nitrogen has 5 valence electrons, and this time there's a lone pair on the nitrogen. So we put 2 non-bonding electrons, and there are 3 bonds to the nitrogen, so there are 6 bonding electrons in total, divided by 2. So 5 minus 2 minus 3 is 0. So then I'll just write all their formal charges below the atoms, 0, 0, 0. So now let's do the same thing for our second structure. We have hydrogen single bonded to a nitrogen, and then it looks like we have, this might be another triple bond to the carbon, and then a lone pair on that carbon as well. So if we calculate the formal charge of our hydrogen, notice that it's the same as the top. There's only 1 valence electron, 0 lone pairs, and 1 bond, so 2 bonding electrons. We still get a formal charge of 0. And for the carbon, carbon has 4 valence electrons. This time there are 2 non-bonding electrons, and there are 3 bonds to the carbon, so we have 6 bonding electrons divided by 2. So this time our carbon, 4 minus 2 minus 3, is -1. So this carbon has a -1 formal charge. Now let's do the same thing for our nitrogen. Nitrogen has 5 valence electrons, and there are no lone pairs on the nitrogen, so we just write 0. And there are 4 bonds to nitrogen, so we have 8 bonding electrons divided by 2. So 5 minus 0 minus 4 is +1. So then if we were to label the charges, hydrogen has 0, nitrogen has a +1 charge. I'm just going to put a plus, and our carbon has a -1 charge. Okay, so these are the atoms labeled with all the charges. So now let's see what the junior tutor said. By substituting the following to the formula given, the formal charges may be determined. So for the first structure, they did it for, okay, so they have all the valence electrons in the same row. And then going down, they calculated for formal charge. 0, 0, 2, 1, 4, 3. And then the formal charges were all 0 for our first structure. And then for the second structure, we have 0, +1, and -1. So this solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a like or comment, or you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.